It's very appropriate to be talking about sea surface temperature at this conference because this has been something that Ariel has had a long history with. In fact, when I was a PhD student quite a while ago, the first visit to another institute I undertook was to R68 here to meet the team behind the long track scanning radiometers. The first instrument in this series is shown in the lab here on the left. And these were particularly accurate radiometers. Really, they took the infrared radiometry from space from being able to support meteorology up to an accuracy relevant for climate, where you need much more accurate data and stability over long periods of time. So for example, this is a movie of some of the climate, of the SST variations in one of the climate data records that we've made at Reading in various projects with ESA and the National Center for Earth Observation. In this particular period, the second ATSR was critical in joining together all the other instruments and be able to create such a detailed and stable data set. So I'm going to be talking about climate change through the lens of sea surface temperature. And you're bound to be aware of the prediction that 2024 will be the first full calendar year that's going to have been warmer than 1.5 degrees above the pre-industrial baseline from the end of the 19th century. Now, the oceans are absolutely critical in climate. 90% of the energy accumulating in Earth's system is accumulating in the oceans. It's really the oceans that drive the rate of climate change. And so it wouldn't be a surprise that the warmth we've seen in this calendar year is really, and last year, is really a reflection of what's happened in the oceans in those 2 years. And that's what I'm going to be talking a bit about. Now, last year was quite a remarkable year. There was a sudden warming of the oceans. It's not often that the Financial Times takes an interest in sea surface temperature, but it was such a remarkable event that even that was possible. Let's actually look at what was so remarkable by looking at the data. So this is data looking at global sea surface temperatures from space. I'm going to call it SST from now on, so sea surface temperature. And these data have been made in ESA project and also extended through the Earth Observation Climate Information Service, which is a program that I'm currently the scientific lead of. And on this graph, we got the years of the 1980s in gray, sea surface temperature progressing through the calendar year for each of those years. 1991 was the year in which the first ATSR was launched. I've colored that in red. And it so happens that in April of that year, the sea surface temperatures were a bit warmer than any other April in that record. And I've shown that record-breaking event in blue just to make it really obvious. So now I'm going to play this movie forward in time. And you'll see that the global sea surface temperature sort of wobbles around. Every so often, there's a special year, 1997, 98, for example, where things get pushed up and they never really fall back to the levels of temperature that were there before. Same happened in 2015, 16, and then we have the last 2 years. And you see that not only were they record-breaking years, they were quite exceptional in how much that record was broken by. Now, of course, this has caused people to ask questions, such as the one we had earlier on. Is something changed? Is global warming accelerating? And that's a question which is still under debate in the scientific literature, I would say. There have been papers arguing that it's just variability and essentially global warming that we've been used to for the last several decades is continuing. There's nothing in that sense to be more concerned about. And basically looking at that question is what I'm going to do today. So this is the sea surface temperature record from space presented in a more conventional way. So it's the time series with the seasonal cycle taken out over the last 45 years. And the question really is, how do we interpret this history? Clearly, there's a tendency for the global SST to be going up over time. And there's all sorts of variability on top. And we understand that variability pretty well. In fact, a lot of it is explicable with just three factors. There's the El Nino events that redistribute heat across the Pacific Ocean. If you lag the index of that, you get quite a good predictor for changes in global sea surface temperature. Then there's the sunspot cycle. We saw that two talks ago, which also changes the solar irradiance, and that's evident in this record. And then there are big volcanic events, and in this time period, particularly the one in 1991 from Mount Pinatubo. So three factors explain most of this variability. And then an underlying trend, and we put those factors together, it explains quite a lot of that history. So the blue line in the top panel is the same data as in the previous slide. And the orange line is the sum of the components from those different factors that are shown in the panel below. Three factors for variability plus just a steady trend. And it looks like a pretty good representation of what's happened. But if you look carefully, you'll see that there are periods where there's a systematic difference offset between the blue line and the orange line. And in particular, the last couple of years, 23, 24, are not particularly well captured by this model of what's happened. And that's a hint that perhaps this straight line rise of global warming is not not the whole story. Let's think a little bit, let's think of it from the other direction. Under what circumstances would we expect global warming to be rising steadily over time? Well, the planet's warming because there's an imbalance of energy between what's being absorbed from the sun and what the planet's able to radiate out to space, given that we've increased the greenhouse gases in the atmosphere. And that imbalance, Earth's energy imbalance, EEI, if that were constant in time, and if the same fraction of that energy were always going into the upper ocean, put those two things together, and you would see a steady warming of the ocean over time, because a similar amount of energy is going into the ocean and warming up in proportion. So those are the two factors that we need to, in the long run, be present in order to see a steady global temperature increase. And is that actually what's going on? Well, we have access to the Earth energy imbalance through another satellite-derived data set, this time from NASA, also using measurements of ocean heat content to calibrate this time series. And it looks like this. Now, there's a lot of variability. It's a very chaotic system, the Earth. It's lots of variability there. But you can see there is a tendency for the Earth energy imbalance to have been going up over time. And in fact, over the last 15 years, that rate seems to have taken a bit more of an uptick. So EEI has not been constant. So we don't really expect, therefore, global warming to be progressing at a steady rate. And in fact, if we add up the energy along this time series, we'll get the accumulation of energy in the Earth system, and that looks like this. If a constant fraction of this accumulating energy is going into the upper oceans, we expect the underlying rate of global warming to look more like this curve rather than a straight line. And as you see, that means that the underlying tendency of global warming would be in acceleration. So we can test whether this better represents the data by putting this back into our model and seeing whether it accounts for the time series better. And it does, particularly the last 2 years, we have a closer representation of the extreme warmth of 2023 and 2024. And so this is also a very statistically superior fit. So this is evidence that we have this picture of a slow acceleration and the variability that's been hiding that acceleration, but the acceleration signal is now evident underneath that variability. That raises the question about what's going to happen next. And the usual way that's addressed, of course, is by looking at projections using climate models. But I think it's also useful to look at recent data and think about what that might suggest and think about a data-driven projection of what might happen in the future. So to do that, we need to think about what may happen to the Earth energy imbalance in the future. So this is the NASA data again in orange. and 3 what-if scenarios for the future of Earth energy imbalance. One is I've called on trend. That's taking the trend of the last 15 years and just projecting that forward into the future. That's probably pessimistic because there's reason to think that some of that uptick in the increase in Earth energy imbalance is due to one-off changes in air quality regulations around the world. The second projection is based on a reversion to the same trend as we had in the 1990s and early 2000s and taking that trend forward in time. And then the third scenario here is a representation of what happens or what might happen if the rates of decarbonization across the world increase significantly and we really reduce the rate of greenhouse gas emissions significantly over the course of the next 5 to 10 years. And in time, that would start bringing Earth energy imbalance down again, which is what needs to happen in order for the climate to stabilize. So putting these what-if scenarios, not really predictions, but they're plausible what-if scenarios for the future into that model for global sea surface temperature and also using what we expect the solar cycle to do, we see that we have this cluster of trends for the future of global SST, which are really quite different to what you get if you extrapolate from the past to the future using a straight line, which is the brown curve here. So with this picture of what's driving global sea surface temperature change, there's an important point that if we're calibrating our expectations of global warming for the last couple of decades against, for the next couple of decades against our experience of the last 40 years or so, we're in danger of underestimating the rate of climate change and the rate of impacts of climate change that are going to come along the track. Another thing to say is that we shouldn't be misdirected by the fact that the future scenarios don't look that different by 2045 into thinking that climate mitigation is not that effective. It's not valid to take a data-driven model like this and extrapolate it too far ahead. So I haven't gone very far ahead in time, but the difference between decarbonizing by the middle of the century or not is the difference between the climate stabilizing for the second half of the century or continuing to accelerate away from us. And so that doesn't detract from the importance of mitigation in any means. So global mean sea surface temperature has been quietly accelerating underneath all this natural variability, I think, for the last 40 years. And we can now detect this acceleration unambiguously in the climate record. That means that the recent past is not a guide to rates of change in coming decades. Let's unpack some implications of that. So we may not be thinking about preparedness for climate change as rapidly as perhaps we should. And also the danger here is that we're underestimating the importance of mitigation because it doesn't seem as urgent as perhaps it should be. As well as underestimating the future of climate change, I think also looking around, people also underestimate our agency to do something about this problem. Just this weekend at a social event, someone said to me, "You must get frustrated that no one's doing anything about climate change." And sometimes it can feel like that. But actually, I pointed out that although action on climate change is nowhere near fast enough, a big multiple too slow to stabilize the climate in the coming decades as we would like so far, actually a lot is happening. The switch to renewable energy that we see in the UK is a worldwide phenomenon. And I think many are underestimating how profound a transformation that is going to be. It's already having an effect on, a measurable effect on greenhouse gas emissions. I'm pointing that out, that both that climate change is big and scary and difficult and it's coming towards us, and that there's already action that is having a measurable impact, that's having a positive effect, was much more encouraging than just the scary message. Because it's much easier to get behind something if it's ongoing and you can put your support behind it. And probably remembering that we have agency to act in this area is something we all need to remember when we think about climate change as well. Thank you for listening.
Thank you, Chris. Some questions. Yeah, please.
That's very superb. Thank you. I feel that I even understand some of it. But there is, in the history of the Earth, the planet, there has been cycles of up and down, and we're obviously on a cycle that's going up, even if we weren't here, I feel. Because if you look back, even the 120 years that we can see that the Earth's temperature is rising very slowly. And I know that we think that dinosaurs were killed maybe by climate or maybe by something hitting the Earth, but things have changed. We've been through ice ages and so on. Do you feel that there is going to be an ice age at some point in the future? And are we nearly there?
So on the first part, the best estimate for the fraction of the global warming that we've seen over the last 50 years or so that's caused by people is 100%. So we need to be clear about that. As for the ice age, yes, at some point in the future, maybe a few thousand years down the line, I don't think we really know when the orbital effects would have kicked in and brought us an ice age. Earth would revert to an ice age again. But that's not going to happen in our lifetime. It's not something we need to think about. And as a species, in any case, on that timescale, we would have to be realizing that we need to control our own climate and keep our Earth habitable for the infrastructure and the quality of life that we're used to. The Holocene, the last 10,000 years since the last interglacial, has been remarkably benign for the whole development of our civilization. And we would probably want to control it to stay within that envelope, no matter what, for foreseeable future.
More questions? Yeah, please. And then in the back, please.
I was struck by the fact that one thing you didn't mention necessarily was tipping points. I mean, there's been a lot of talk about disruption of the overturning circulation, for instance, of the Atlantic, and what that could do in a very short period of time if it actually happened. I don't know whether you care to comment on that.
Yes. One of the reasons that the target range for the international agreements is between 1.5 and 2 degrees is that it's in that range that various tipping points, the first of the tipping points, really begin to kick in. And there's scientific uncertainty about exactly at what thresholds that would be the case and what some of the consequences would be. In terms of communicating that to the general public, as a scientist, I think, terrible. West Antarctic ice sheet will go unstable and we'll be committed to 6 meters of sea level rise. And that's one of the tipping points that will happen between now and 2 degrees. But possibly that takes hundreds of years to happen. Do enough people care about what's happening in a couple of hundred years? I think it's important. Not everybody sees that importance. So one of the reasons I would emphasize the more immediate impacts, such as the fact that rising adaptation costs over the next couple of decades will really be a drag in the economy. That the plans of fossil fuel companies to expand their production and make more profits are essentially a means of making profits now at the expense of all of our future pension savings. I think those sorts of things maybe communicate to a wider audience more. But you're absolutely right. The tipping points is a big issue, and some of them will make stabilizing our climate even harder than it already is, which is a big danger.
There was one question in the back, yes.
Thank you very much. Like the last questioner, I thank you because I actually found that quite easy to follow, but very, very profound and interesting. I just had a bit of a question about whether I'd understood this properly, but I think you were saying that the last 2 or 3 years in particular, the linear model has sort of broken down and not predicted very well the increase in sea surface temperature. I'd also seen that the main reason for the peak in the last 2 or 3 years seems to be the El Nino effect from what you were showing. So to what extent could our failure to model the El Nino effect also be an explanation of what's happened in the last 2 or 3 years?
Yes, the reason that this temperature record has been caused in these last 2 years is because of the El Nino phenomenon of the last 2 years. But there's something like 1/10 of a degree of how warm the last couple of years has been that you cannot explain just from the El Nino plus a linear extrapolation of global warming underneath. Unless you account for this acceleration effect, which I've shown, that 1/10 of a degree that made this last couple of years so exceptional can't be explained. The El Nino of the last couple of years was not particularly strong. It was a major event, but it wasn't as strong as some of the previous ones. And yet you saw that temperature rise was bigger than any of the previous big El Ninos.
Okay, so if I can just come back then, so you're confident in the modeling of the El Nino effect. That's we couldn't be wrong in how much we've modeled the impact of that effect.
Well, it's so the predictor in this model is measurements. That's all observations of the actual El Nino. It's a fit. It means that there's a weighting to that, which in reality is more complicated than one number, but it's represented by one number in this model. So it doesn't fit perfectly, but it is statistically enough to show that there's been acceleration rather than just a steady rise.
Thank you.
I should say that this the work I've shown is in a paper that's still in peer review, so you've got a sneak preview of results that aren't yet published.
One last question right here, and then keep your questions for after the talks.
Yeah, I just wondered if you could say whether there's any 1 or 2 or 3 specific reasons for the acceleration.
We expect, I've shown how it's related to this Earth energy imbalance, and you do expect, you see it in climate models, that over the progression of time, this Earth energy balance is expected to increase. So you see a similar nonlinearity in climate model projections at the high emissions scenarios. And then the additional effect, I mentioned the air quality regulations, that there is some thought that cleaning up that aspect of pollution, so aerosol emissions from China have gone down a lot over the last 15 years. There's less sulfur in shipping fuel than there used to be because of regulation, and that also has an impact on the reflectivity, potentially, of the Earth. It's actually very difficult to pin that down and make join those dots to prove that this has been going on, but that is certainly one candidate factor for why that Earth energy imbalance has been changing a bit more in recent years.